Hello and welcome to this SeaSharp Eurocode9 tutorial episode. It will be about generating load cases. And the first thing I will do then is to open an existing workspace here. And then I will go into the loading folder, the load combinations. And here we have several ways of defining load combinations. And the simplest one is this tabular approach, where you specify the Sestra load case numbers. It may be several, and then you have to separate them with the semicolon. So let's say it's load case number 1 for 6 and number 7, and they have a load combination factor of 1.3 for load case 1, 1.0 for load case 2, and 0.7 for load case number 7, 1.0 for load case number 6. And material factor, ULS condition in Norway, this will be like 1.15. And for the plastic checks, it's 1.38. And then you can continue down the list here, defining lots of loading conditions. Just to give it a point, I will just copy this, Ctrl C, and then just paste it here. I'll just say that, okay, it's not 7 anymore, but it's like 8. And then we say okay. And then we have two load cases. It's the Sestra load case, which is the load case that we ran in the finite element analysis. Typically a basic load case just containing one specific type of load, like gravity or acceleration or wind or some type of loading. And the next type of load combination that we can define is called simple tabular load combination ranges. And as previously, we had to define the material factor for the elastic checks and the plastic checks, and then just the name prefix like ULSA or something like that. And then we define ranges of load cases. And this dialog will actually spin up a lot of combinations of load cases. And if I say like first load case is 1 and the last load case is 3, and they will all have a load factor of 1.0. And then the first load case is 6 and the last load case is 9, and they will all have a load combination factor of 1.3. Then the program will create one load combination for each combination of value from the first load case range and from the last load case range. So if I just say OK now, we will get one combination using load case 1 and load case 6, and one combination using load case 1 and load case 7, one using load case 1 and load case 8, one case 1 and load case 9, and then one combination using load case 2, load case 6, load case 2 and load case 7, load case 2 and load case 8, and load case 2 and load case 9, and so forth. If I just say OK now, we see here we get one load case, which is a combination of load case 1 with load factor 1 and load case 6 with load factor 1.3. And then the next one, which has load case 1 and load case 7 with combination factors 1 and 1.3, and so forth. And now we go into the most advanced way of defining a load combination, and this is specific for the transportation load combinations. And what we are giving in here is several values, but I will first try to explain the challenge and the idea behind this. And the transport load case, it will typically consist of gravity loads, of a vessel acceleration. So we are talking about an offshore transportation here, or it could be an acceleration of a trailer or some land-based vehicle as well. And then there are wind loads, and there may also be other loads. And the challenge is how you combine these with different vessel headings and wind up and down and in different directions. And you get a huge number of load combinations when you try to combine all these with the correct load factors. So the approach that you need to use here is that in the finite element program you have to run load cases with unit acceleration in the xy set and rx, ry and rz direction, separate load case for each direction. And similarly for the wind, you have to run one separate load case with wind in each direction. But here you don't apply just a unit wind velocity, but you apply the actual wind velocity. And in addition, you will need to run two load cases with wind up and down on large flat structures like a helideck or similar. And if these are not present, you need to run dummy load case with zero load for these ones. Now going back here, we defined a load factor for the environment, which is the wind and the vessel accelerations, which may be 0.7. And we defined how the structure is positioned on the vessel, the rotation between the vessel coordinate system and the structure coordinate system. So if the structure is rotated 90 degrees on the vessel, this will be 90 degrees. Then we define the vessel accelerations for different headings. And I have a table here with these values for this example. So here is only the x and y accelerations that have been defined. So I paste them in here, like this. And then it's the acceleration basic load cases that we run in the finite element program. Research sway here, roll, pitch and yaw. And for this case, these load cases, I have them here, basic load cases. So I will paste them in here. And then we have the load cases for the wind load case, and the load case for the large flat structure like the helideck. And then again I will just copy these values from this spreadsheet like this, and we'll take them here. And then if there are additional load cases like or you always need to define at least one additional load case, and that is the gravity. And this also defines the material factor. So the elastic material factor and the plastic material factor. And the name transit. And this is just one load case, and that's the gravity with a combination factor of 1. And this completes this load combinations, and I just say OK. And now the program generated a bunch of load combinations here, corresponding to the different acceleration directions, headings, and wind directions.